I looked it up on your website, and apparently I missed the connection. So you joined in. I thought you joined in April. When did you join? Oh, both of these. Okay. All right. Good. So we got that straight. He is very diverse in his interests. We've worked on the weak interaction side, and so what you're going to present today is about the strong interaction side of nuclear science. And it's this interesting problem of how you get the spin of one hit hbar for the proton from quantum field theory from all the gluons and quarks that are inside the proton. And here's Carl.
Hello, do you hear me in the back? You hear me in the back now? Okay. Pleasure to be here today to tell you about what we're learning to try and find out what makes the proton spin. Today I'll start out with an introduction. Then I'll talk about longitudinal spin structure, and I'll define what I mean by that when I get there. And I'll follow that up with some discussions about transverse spin structure of the proton, and I'll define that when I get there. So the proton, we've understood since the 1960s, is made of quarks. We have two up quarks and a down quark. You put them together and explains all the proton quantum numbers: charge, parity, spin. Spin is a particularly interesting and useful tool in looking at this because we know that it arises from intrinsic quantum mechanical dynamics. Spin doesn't have a classical analog. We think of a top, but it's not a top. Now, if we write a static quark model wave function for the proton, it ends up looking like this. Those of you who are going to be stuck with me in 414 next fall might get this for a homework question. It turns out that if we take those three quarks and you set the mass of the up quark and the mass of the down quark both equal to 1/3 of the mass of the proton, and then you calculate the proton magnetic moment that would come out, you get 3 times the nuclear magneton, when the real answer is 2.793. You get minus twice the nuclear magneton for the neutron, where the right answer is minus 1.913. Clearly, they're both quite close. The ratio actually matches to 3%, and the numerical values are within 10%. And in fact, if we allow for the quarks to be slightly heavier than the proton mass over 3 to provide some room for binding in a conventional sense, turns out we can match these observed magnetic moments extremely well. But this is clearly too good to be true. The proton radius, actually that number has considerable controversy at the moment. It's approximately 0.85 Fermis, although a recent measurement came out 7 sigma away from the world average, and that is currently under investigation. It's still 0.85. We're talking about a difference of a few hundredths of a Fermi, but that is 7 standard deviations for that number. If we put quarks inside 0.85 Fermis, turns out the Heisenberg uncertainty principle says that quark motion has to be relativistic. That means we need a relativistic quark model instead of a static quark model, and once we do that, the quarks are no longer restricted to S-wave states. Turns out they no longer provide the proton spin. They only provide about 60% of it. And the rest of the proton spin comes from quark or orbital angular momentum. With the relativistic motion, you end up with mixing SP wave interactions from the fact that J is the good quantum number. L and S are not individually good quantum numbers. The system has spin of a half, but the individual constituents get confused, would be a way to think of it. Yes? That comes from generates the large orbital angular momentum contribution. Correct. Total angular momentum. We'll get to that. We'll get to that. There are no binding forces in these calculations. It's just put in a bag. The strong force provides the binding. The strong force comes from quantum chromodynamics. Quantum chromodynamics binds quarks by the exchange of gluons, so there have to be gluons present as well. And it turns out that when that happens, there are also additional quark-anti-quark pairs in addition to the two quarks and the two up quarks and the down quark that we started with. So it starts to become a considerably more complex object. So the question becomes, how can we look inside the proton and explore this structure? Standard tool that's been used for 5 decades now is deep inelastic scattering. We take an electron or a muon beam. My battery must be dying. Scatter them off of protons. Basically, that occurs through the exchange of a virtual photon. That virtual photon is electromagnetic. It interacts with charges. The charges in the proton are the quarks and the anti-quarks. Essentially, this is an ultra-relativistic version of Rutherford scattering. And just as Rutherford scattering let us look inside the atom to see the nucleus, this lets us look inside the proton to see the quarks and the anti-quarks that are there. And it's told us a great deal about the internal structure of the proton. Of course, no. Top one. This is a better laser pointer. Okay. The interaction is electromagnetic. So only the quarks and the anti-quarks participate. Gluons don't. We only obtain information about gluons indirectly. The way that happens is through what's called evolution in quantum chromodynamics. If we examine the proton and the hydrogen atom very closely, we see that the virtual photons that surround that charge split into electron-positron pairs, the standard vacuum polarization phenomenon, where a virtual photon splits into an electron-positron pair and can recombine back to the virtual photon. The same thing happens if we examine in quantum chromodynamics a quark or a gluon on a small scale. A quark can split into a quark plus a gluon. A gluon can split into a quark-anti-quark pair, or it turns out a gluon can split into two gluons. This is the non-abelian feature of the strong interaction. This is the thing that isn't there in electromagnetism. Photons couple to charges. Photons don't couple to other photons. But gluons do couple to other gluons. So if we explore on a very small scale, as we probe more deeply, turns out that the number densities of the quarks and gluons that we see increase due to this splitting. But of course, energy and momentum has to be conserved. So on average, individual quarks and gluons end up carrying less momentum when we're looking at it on a finer scale than when we're looking at it on a coarser scale. As a practical matter, what that means is that if we start with our proton and we look at it on a very coarse scale where we see the 3 quarks, as we look on a finer scale, we see a lot of substructure with extra quark-anti-quark pairs, with gluons, as well as the original 3 quarks. And of course, identical particle says, I can't tell the difference between my original up quark here and an up quark over here. So, when we do those measurements, we extract what are called Parton distribution functions. This is the cross-section for that deep inelastic scattering. Scattering, in this case, of electrons and positrons off of protons, done at the Hadron Collider at DAISY. These cross-sections get interpreted as the density. The cross-sections are related to the quark densities, the charges that are observed. This gives us the probability of finding a quark or a gluon inside the proton fit carrying some fraction, x, of the total momentum that the proton carries. Here's the fit, and this fit here, which has ballpark 20 parameters, gives this fit to the experimental data, describes it beautifully. Turns out that in this parton distribution function, the probability of finding quarks and gluons in the proton, we actually find more gluons, that's this curve here, than anything else. And it turns out that if we integrate the momentum of all of these guys, the gluons actually carry half of the momentum of the proton. The quarks and the anti-quarks carry the other half. Now, I told you we get gluons indirectly through evolution, through this splitting process. That's embedded in these curves here. Each of these is at a fixed momentum for the struck quark or anti-quark as a fraction of the proton, but for different transverse momentum, basically different probing scales. When we probe at a finer scale, we see the higher density of softer, lower momentum quarks. It's basically the square of the wave function. It's a number density. It's a probability. As a function of, now this x here is the momentum carry. It's a function of the momentum carried by the quark or the anti-quark in momentum space. So it's the square of the wave function in momentum space. Oops, wrong way. In this scattering process, from the yield here, that tells us essentially the strength of the charges that we scattered off of. From the kinematics here, the outgoing energy and momentum, since in deep inelastic scattering, this is basically a 2-to-2 elastic scattering process where the electron or muon elastically scatters off of the quark. By measuring one, we can calculate explicitly the kinematics of the other, and in turn figure out how much momentum this quark or anti-quark brought into the collision. Note that this doesn't tell me whether this is a up quark or an anti-up quark, because it's electromagnetic, so it's coupled to the charge squared. But the cross-section for quarks and anti-quarks are the same, but the cross-section for U quarks and D quarks are different. This is an electromagnetic interaction. This interaction is well understood, and it's rather weak. Virtual photon, if you go down in energy, you need to worry about multiple photon exchange. But it's sufficiently high momentum transfer, multiple photon exchange is negligible compared to single photon exchange. And that momentum transfer is encoded in this horizontal axis here. And basically, the data where you need to worry about the kinematics, where you need to worry about multiple photon exchange, has been cut off the bottom of the plot. That's right. In this case, just the photon. Because we've got an interaction. In principle, there can be Z0 bosons exchanged, and that is actually included in the calculations. Although they make a negligible contribution. There can also be W bosons exchanged. Then you see a different final state, and that's actually explicitly identified, and that does make an interesting contribution here when the exchange is a W boson. As I say, the Z can interfere with the gamma, and that is included in the calculation. At these very high momentum transfers, that's a non-negligible probability. Down here, the Z makes a negligible contribution. So, that's electron, deep inelastic scattering, electron or muon, leptons scattering off of protons. PP collisions can also contribute. And in quantum chromodynamics, the way we picture a PP collision, we have our two protons, each of which consists of a bunch of quarks and anti-quarks, or gluons. We take a quark or a gluon, aka a parton, from one of the protons. We take a quark or a gluon from the other proton. The probability of finding those quarks or gluons in the proton with particular fractions of the proton momenta are given by those parton distribution functions that we saw in the previous slide. The quark or gluon then interact with each other, in this case through a strong interaction. And that cross-section, so long as the momentum transfer here is sufficiently large that the strong coupling constant is small compared to unity, that cross-section can be calculated using perturbative quantum thermodynamics. As a practical matter, that means this momentum transfer needs to be several GeV over C or larger. Once we scatter, we have two outgoing partons, quarks or gluons. Those are colored objects. In the world, we don't see colored objects. We only see neutral colorless objects. So those quarks or gluons end up fragmenting into a bunch of hadrons that come out in a collimated spray that we call a jet. And measurements can be done adding up all the hadrons to make a jet or grabbing one of the hadrons out of the jet. And it turns out that for the measurements I'm going to be telling you about at RHIC, Phoenix tends to specialize at grabbing one of the hadrons out of the jet, while star specializes in adding all the hadrons together to construct the jet as a whole. The key point here is that because these can be either quarks or gluons or a combination, we have quark-quark scattering, quark-gluon scattering, and gluon-gluon scattering. They all contribute. And that's quite different and complementary to the deep inelastic scattering. In the deep inelastic scattering, we saw we're sensitive to electromagnetic interactions. We can also be sensitive, as I said, to weak interactions. Electromagnetic interactions, we're measuring charge squared. We have no sensitivity to the color of QCD. Weak interactions are measuring the weak charge, which basically means the flavor. It also is insensitive to the color of QCD. The strong interactions are specifically sensitive to the color, and because of that, because the gluons carry color, but they don't have weak charge and they don't have electric charge, the strong interactions give us unique sensitivity to the gluons. The strong interactions doesn't care whether we have an up quark or a down quark. They are insensitive to the flavor. So to get a complete picture, we need to put them both together. And in fact, when we do that, when we combine them, we get additional opportunities. We can explore so-called universality. We can ask, do the parton distribution functions that we see here, do we get the same ones down here or not? That helps us separate phenomena that are intrinsic to a particular interaction versus those are the intrinsic properties of the protons that we're studying. So the tool that I use to do this is the Relativistic Heavy Ion Collider at Brookhaven National Lab. As the name Heavy Ion Collider implies, it was designed to perform heavy ion collisions to search for the quark-gluon plasma and study its, and these days we've seen it, and we're now studying its properties. That's what Saskia does. It was also designed to explore the partonic structure of the proton. That's what I do. And to determine the partonic structure of nuclei, and I've done some of that in the past, although I haven't been doing that recently. This is an aerial photograph. RHIC is a 3-ring circus. The beams are produced over here, and they go around one ring and get speeded up. They go around another ring and get accelerated. They go around the 3rd ring. Actually, it's a 4-ring circuit, because up here we have, up here we have 2 rings, one that goes around counterclockwise, one that goes around clockwise. And those 2 rings cross each other at 6 points, and those are where collisions occur. That's actually G-2, and that's from a former experiment, which is no longer located there. It has now been moved to Fermilab. There are 2 large experiments at RHIC, the Phoenix experiment and the STAR experiment. Truth in advertising. Phoenix is a beautiful detector. It's done a bunch of gorgeous measurements over the years, but the fact is, STAR is the star at RHIC. I'm a member of STAR. RHIC, in addition to being a heavy ion collider, is the world's first and only polarized hadron collider. We start with polarized ions and we run them through this 3 or 4 ring circuits, accelerating them while starting with polarized protons, preserving their polarization through the, or at least most of their polarization, through the acceleration process, all the way up to energies of 100 GeV per beam. That's about 107 times the mass of the proton, or 255 GeV per beam, giving us collisions at 200 or 500 GeV per nucleon, center of mass energy. There are various tools that help us preserve that polarization, including funky things called Siberian snakes, which actually flip the beam spin every time the beam goes through. So every time a proton goes around the ring, it gets its spin flipped twice. That's a trick that helps preserve the polarization. There are 120 bunches of protons circulating in each of these two beams. Bunches sequentially collide at either star or phoenix, and we can control the spin on a bunch-by-bunch basis, which means that we're flipping the spin at star or at phoenix as often as once every 106 nanoseconds. We change the pattern of how we align the spins within that 120 bunches on a fill-by-fill basis. Each fill lasts typically 8 hours. We have things called spin rotators that sit on each side of star and each side of phoenix. The stable polarization direction in the ring has the spins of the protons transverse, vertical, perpendicular to the ring. If we want to study transverse spin structure, we're good to go. If we want to study longitudinal spin structure, we need to take those proton spins and reorient them so that they are longitudinal along the beam direction instead of perpendicular. And we do that with the spin rotators. We rotate the beam from transverse to longitudinal. It goes through star, and then we have to rotate it back from longitudinal to transverse again to go around the ring and preserve its polarization. We have the ability to choose whether we want to run transverse or longitudinal at star. Phoenix has the choice to do transverse or longitudinal at Phoenix. It turns out right at the moment we're running both transverse, but as of a week from today, star will be flipping to longitudinal and Phoenix will be staying transverse. Beams go around here 70,000 times per second. 8 hours, that translates to something like 4.5 billion spin flips, because they flip twice in every rotation. Very little depolarization. The polarization, which starts out typically at 60%, decreases by about 0.75% per hour. The spin dynamics in this ring are extraordinarily well understood. So now let's talk about longitudinal spin structure. Here I'm talking about helicity distribution. I've told you about parton distributions. If I imagine that my proton is moving toward the right and its proton spin is also pointing toward the right, so the proton has positive helicity. The parton distributions, or PDFs, measure the density of the quarks and gluons in the proton independent of the direction of the spin of those quarks or gluons. So we take the number of quarks or gluons with their spin aligned parallel to the proton spin, the number with their spin aligned anti-parallel to the proton spin, and we add them together. And we get something we call Q as a function of X or G as a function of X for quarks or gluons. And this Q could be a U for an up quark, it could be a D bar for an anti-down quark, or whatever. If we, instead of taking the sum of those, we take the difference, we're measuring the polarization of the quarks and gluons inside our polarized proton. And these are the helicity distributions, delta Q or delta G. They're often also referred to simply as the polarized PDFs instead of the unpolarized PDFs. Again, how do we see that microscopic origin of the proton spin? We use deep-inelastic scattering again. Except this time we take our lepton, our electron, or muon, and we polarize it. And we take our proton, and we polarize it. And we go through the scattering process. If our electron or muon is longitudinally polarized, and our proton is longitudinally polarized, when the virtual photon is produced, it turns out that virtual photon carries a significant longitudinal polarization of its own, which can be calculated in quantum electrodynamics. That gives me a virtual photon that, for example, has its spin pointing to the right. Photons have spin 1. So the Z component there is +1. If I have a quark here coming along, and its spin is pointing to the left, parallel to, say, the proton spin up here, then the total z component of the spin here is 1/2. If its spin is pointing in the opposite direction, if its helicity is negative, then these two add and we get a total spin of 3/2, and the cross-section for scattering in the 1/2 and the 3/2 states are different and calculable in QED. So by measuring the difference in the cross-section for like helicities, that would be this and this, versus unlike helicity beams, that provides information about the orientations of the spins of the quarks inside our polarized proton. The first measurement that ever did this over a broad kinematic region was performed by the European muon collaboration about 30 years ago. Here's their result, which is one of the most famous results in all of high-energy nuclear physics. They measured the scattering difference as a function of the momentum carried by the quark or anti-quark that was struck. And then they calculated the integral from some minimum value to 1 of this distribution. That integral is related to the total polarization, total spin contribution that the quarks and anti-quarks combined make to the spin of the proton. And you see the integral nicely saturated at about 0.115. Fine. The problem was what was expected from that relativistic quark model was 0.19. What was seen was only about 2/3 of what was expected. And when that got cranked, it turned out that the quarks only contribute 14 plus or minus 9 plus or minus 21% of the proton spin. This became referred to statistical and systematic. This systematic uncertainty in this case is largely dominated by the uncertainty in extrapolating to x equals 0. This was called the proton spin crisis because everybody knew the spin of the proton came from the quarks, but suddenly the quarks might contribute nothing to the spin of the proton. Very bizarre result. Well, there have been lots and lots of subsequent measurements. Here's that original EMC measurement. Here are a whole bunch of other measurements that have been done since then of deep inelastic scattering. There are a comparable number of measurements that have been done of so-called semi-inclusive deep inelastic scattering. That's where you observe the scattered lepton, but you also see a hadron from the scattered quark at the same time. And you take all of those results from all these different experiments, hundreds and hundreds of data points. You throw them into a global analysis that finds a best fit for the polarized parton distribution function. In this particular case, there are about 14 parameters in the fit. There are 410 data points in the fit. And you see the description of the data is extremely good. And you infer what the polarized parton distributions look like. And here's what this particular fit got. Polarization of up quarks plus anti-up quarks is extremely well determined. It's positive. The up quarks and anti-quarks have their spins pointing in the same direction that the proton spin points. The down and anti-down quarks have their spin pointing in the opposite direction from the direction the proton spin points. They're also well determined, but not as well as the up quarks. If we ask about anti-quarks, they are not nearly as well determined. Note the vertical scale here has been amplified, but these uncertainty bands are much larger than these uncertainty bands. That's because the deep inelastic scattering, remember, is primarily sensitive to the quark charge squared. So the deep inelastic scattering doesn't distinguish between U and U bar, or D and D bar, but it does distinguish these from these. Only that semi-inclusive deep inelastic scattering, where an outgoing hadron, maybe a pi plus or pi minus, is observed, allows one to separate U from U bar, D from D bar. There's less data there and much more larger uncertainties, so these have bigger uncertainties. In turn, the individual up U bar, D, D bar helicities have much larger uncertainty. And if we put all this together and we ask what fraction of the spin of the proton comes from the spin of all these quarks and anti-quarks combined, it's about 30%. So in other words, When we add all the spins of all the quarks and antiquarks together, we don't get hbar over 2. We get hbar over 6. Hbar over 3 is missing. So some fundamental questions. How do the quarks and gluons conspire to provide the proton spin of 1/2? What's the role of gluon spins? Quark spins provide about 1/3. What's the role of antiquarks? As you saw, those uncertainties are quite large. What about the orbital angular momentum? Of course, to get at orbital angular momentum, we need to look at correlations between position and momentum. We need to see orbiting. So can we correlate quarks and gluons in coordinate space with their behavior in momentum space? And it turns out that in the process of working toward this, a cute thing you're going to see at the end is we can actually visualize color interactions in quantum chromodynamics. So, what about gluon polarization? Remember these unpolarized parton distribution functions, which are determined with extraordinary accuracy. There's a huge body of data. In contrast, the data from polarized PDF bits are far more limited. In fact, there's the kinematic region. Remember that the way the gluon polarization is determined is through these evolution effects, which are basically measuring the slopes of these curves. With a very short lever arm, those slopes are determined very poorly. In turn, if we ask for what the gluon polarization looks like, here we're looking for this total spin of 1/2 hbar. It has to come from the spins of the quarks. The half is because each quark has a spin of 1/2 hbar, and delta sigma is the polarization of the quarks, which we saw is about 1/3. So there's our hbar over 6. Gluons have spin 1, so we take the full polarization of the gluon, and then there's the possibility of orbital angular momentum. We put those all together, we better get 1/2 hbar. Well, here's a fit to the polarized deep inelastic scattering data where only the lepton was observed. This was done just in 2010. It found this result for the spin of the gluons as a function of momentum, the polarization of the gluons with a large uncertainty. If you integrate this, it concluded that the gluons contribute 0.46. That's 0.46 hbar. In other words, the entire spin of the proton, with an uncertainty that goes from 0, the gluons make nothing, to twice the spin of the proton. Clearly a problem. Here's another fit done by a different group, also in 2010, where they used the deep inelastic scattering data plus the semi-inclusive deep inelastic scattering data. This is where both the lepton and a pi plus or pi minus were observed simultaneously. And they found 2 fits of equal quality. Formally, there were about 850 degrees of freedom in their fit. They had 16 parameters in their fit. And the chi-square for the 2 solutions differed by 4 in 850. One of the solutions had the gluon polarized positive at all momenta with an uncertainty band given by the dotted curve. Concluded the gluon contributes 2/3 of the spin of the proton with an uncertainty of a comparable magnitude. The other fit of equal quality actually had the gluon having a complicated structure with positive polarization when it has a large fraction of the proton momentum and polarized in the opposite direction from the proton spin when the momentum is small. And it turns out that this actually integrates to a much bigger contribution than this. So in this case, the gluon contribution was 2/3 of the spin of the proton, pointing opposite to the spin, which combined with the quark spin of 1/3 of the spin of the proton would actually leave us with a net negative polar contribution from all spins combined. Again, in this case, with an uncertainty equal to the entire spin of the proton. Obviously, deep inelastic scattering isn't going to tell us much about the spin of the proton with the existing data. But it turns out we can explore gluon polarization extremely well at RHIC. The measured quantity we use to do that is called the longitudinal double spin asymmetry. It's the difference between the cross-section when the helicities of the 2 beams are equal, minus the cross-section when the helicities of the 2 beams are opposite, divided by the sum. That ratio ends up being proportional to the ratio of the polarized parton distribution to the unpolarized parton distribution for the 2 flavors of partons which are contributing to the collision times ALL hat that I'll get to in a second. At RHIC, we can look at gluon-gluon scattering, quark-gluon scattering, and quark-quark scattering. We can't distinguish which happens. But we can calculate probabilistically what's going on. And here's the probability that we had a gluon-gluon scatter. Here's the probability we had a quark-gluon scatter. Here's the probability we had a quark-quark scatter. As a practical matter, you don't see it from this plot, but by the time you're up here, there's no cross-section left. So in practice, we're completely dominated by gluon-gluon scattering and quark-gluon scattering. Now, when two gluons collide with each other, if the two gluons are polarized, then the cross-section difference for those two gluons is given by the ALL hat for the two gluons, which is this red curve here. And this asymmetry peaks up at 0.8. That's a huge asymmetry. If we have a quark scattering with a gluon, the asymmetry is this blue curve here. And the most relevant kinematic region ends up being sort of in the middle of this, where the two quarks or gluons come in and they collide and they go out at 90 degrees in the center of mass frame of the parton-parton frame scattering. That's not always the center of mass frame of the two protons in the lab. And again, very large asymmetry. So we have large asymmetries, large sensitivity in the cross-sections for the scattering of the individual partons. We know already a lot about the quark polarization. That lets us bootstrap. We have high probabilities for gluon and quark-gluon scattering. We put all that together, and when we measure this ALL for pions, that's one hadron out of our jet, or full jets, it ends up being very sensitive to gluon polarization. So the first polarized parton distribution function analysis that ever used RHIC-PP data was done in 2008 by a group called DSSV, with Florian, Sasso, Stratman, and Vogelsson. Here are the data that they used from RHIC. There were approximately 440 data points in their fit. About 40 of them came from RHIC. These are pion measurements from Phoenix. These are jet measurements from STAR. You see the curves that are the best fit to the data, and the yellow band is their preferred uncertainty range. You see that they fit the data quite well. The gluon polarization that they got ended up having this funny nodes type structure. Again, the yellow band is the uncertainty. And here is the chi-square probability distribution for the total fit, and it's completely dominated over here by STAR data, and on this side, there's sort of equal contributions from deep-inelastic scattering and from RHIC data, which is combined STAR and Phoenix. Their conclusion was that in the region that is sensitive, the polarization was not large, certainly a lot smaller than that inclusive deep-inelastic scattering fit from 2010 that came up with the full spin of the proton, plus or minus the spin of the proton. That was from data that were recorded in 2005 and 2006. We revisited things in 2009. And the results from 2009 for both Phoenix and STAR were published last spring. Phoenix pions and STAR jets. Here are the results. This is the Phoenix pion asymmetries. They're more or less consistent with zero. This dashed curve is the prediction from the previous fit. Here are the STAR jets. Different kinematic regions, different momenta for the jets. And if I go back, and remember this yellow band here, it's sort of a triangular band. Here that triangle basically sits on the horizontal axis, and the upper limit goes just a little below the red curve. So the uncertainty region from data recorded through 2008 was this full big triangular region, and the data from 2009 draw a very narrow road through that previously allowed region. Substantially more precise than the results from 2005 and 2006. In fact, in the case of STAR, we ended up recording 20 times the statistics that we had in 2006. Those have already, even though they're just released a year ago, been plugged into global analyses to extract the gluon polarization by not one but two groups. The DSSV group, as well as a group, NNPDF. The NN in this case doesn't stand for nucleon-nucleon, it stands for neural network. The DSSV group and the neural network PDF group have both plugged the RHIC data that were released last spring into their global analyses. They both find that the RHIC results provide significantly tighter constraints on the gluon polarization than previous measurements. Here is the best, this new red curve is the best fit now from DSSV. Their old best fit is this black dashed curve. Their 90% uncertainty band is given by the envelope of these dotted curves. And you see regions of the old fit are now excluded at the 90% confidence level. You also see that the node has gone away and the gluon polarization appears to be positive everywhere. The NNPDF, the previous fit, which used only inclusive deep inelastic scattering, had the green region for the gluon. The new fit that includes the RHIC data is this red band. Substantially reduced uncertainties in the region that the RHIC data are sampling, which basically starts about here and goes up. And again, we've shifted from something that more or less straddled zero to something which is clearly positive. We integrate the region where the gluon carries a momentum of at least 5% of the total proton momentum, and DSSV finds the polarization, the integral of the gluon polarization is 0.19 plus 0.06 minus 0.05, and NPDF finds 0.23 plus or minus 0.27. These are, again, in units of hbar. So X is the fraction of the momentum of the proton, which is carried by a single gluon, the gluon that's being studied. So here, this 0.23 is 0.23 hbar. So that's half the spin of the proton, and more than we see from the total quark contribution. Of course, if I add a half and a third, I get 5/6. And that's getting close to the full spin of the proton. And we haven't extrapolated down, but you can see the extrapolation uncertainties are quite large. So there's certainly still plenty of room for orbital angular momentum. Where to from here? This in the DSSV represents the uncertainty in the integral. This is in the region that RHIC samples from 0.05 to 1. And you see the region allowed at 90% confidence. And this represents the integral below the region that we're sampling with the data that we've recorded to date. And you see the uncertainty suddenly explodes. Goes from minus 0.3 to plus 0.8. That would represent a spin that's 1.5 times the total spin of the proton. So we clearly need to extend our measurements to lower gluon X values, where the current extrapolations have very large uncertainty. We need to narrow this band here. And we have first measurements that are now doing that. We had very successful runs with higher energy proton beams during 2012 and 2013. Turns out that those higher energy beams probe lower momentum quarks and gluons. And here are Phoenix Pions, and here are star jets. They were both released recently, actually last October, a few minutes apart at the same conference. Here are the data. The blue points are the points I showed you a few minutes ago from 200 JeV. The red are the new measurements at 500 JeV, and the curves are the models that describe the 200 JeV data well, and they're just laid on top of the 500 JeV data, and they do very well. The new results are well described by the global fits that previously gave a good description of the 2009 results. These have not yet been folded into a global analysis. Additional future measurements are going to try and squeeze this uncertainty band down in both directions. Phoenix is analyzing data that they recorded in 2013 that should squeeze down this way. I told you that STAR will be rotating our spins from transverse to longitudinal next Thursday. That's in order to repeat the 2009 measurement with improved precision to squeeze this down this way. And in the further future, both Phoenix and STAR have proposed significant upgrades in the forward direction for around 2020, motivated by spin and proton nucleus measurements. And it turns out that forward dijets will directly measure the gluon polarization all the way down at an x of 10 to the minus 3 with very good precision. Now, I've been talking about gluons, but it all started with the quark contribution. The quark spin, delta sigma, being 0.3. Why is it so small? Delta sigma is the sum of the polarizations of the U and the U bar quarks, the D and the D bar quarks, the S and the S bar quarks. Add them all up. Polarized inclusive deep inelastic scattering measures this combination and this combination. Polarized semi-inclusive data provides some flavor separation, but as you saw earlier, the uncertainties remain large. Turns out that an experiment that actually Bob Tribble and I were involved in 15 years ago, Fermilab 866, found surprising structure in the unpolarized anti-quark distribution. This is the ratio of the unpolarized d bar over u bar as a function of momentum, and we found this unexpected structure with a very large asymmetry between the number of anti-Ds and anti-Us, which begs the question, might the polarized anti-quark distributions also contain surprises? It turns out that at RHIC we can separate polarized quark and anti-quark flavors with W production. W's are made in weak interaction. The weak interaction is a pure V minus A. So we have only left-handed quarks participating and only right-handed anti-quarks participating. It's a perfect spin separation. It's complementary to semi-inclusive deep inelastic scattering, and it's extremely clean, theoretically. And this is the first results from STAR that were published last year. The green was the expectation from semi-inclusive deep inelastic scattering. The solid boxes show the asymmetries for W+, and they follow the model predictions very well. The open boxes show the asymmetries for W-, and they sit on the upper edge of the previous uncertainty band. Again, they've already been plugged into a global analysis by the NNPDF group, and what they find is that the W's minuses lead to a significant increase in the polarization of the U-bar. Here, because it more or less agrees, we just have a narrowing but not a significant change in the central value for the D-bar. The unpolarized distributions have D-bar bigger than U-bar. The RHIC results are pointing to delta U-bar larger than delta D-bar, the other way around. And additional precision is coming soon. What you saw were results from STAR from 2012. STAR recorded 3 times as much data in 2013, and Phoenix has all of the 2012 and 13 data. We put that together. These are the sort of uncertainties we're expecting. And here are in a chi-square analysis, here's what we knew about the U-bar and D-bar before the RHIC data. And here's what is expected in a chi-square analysis after all of these data are finally analyzed and included in global analysis. It's also worth noting that these uncertainties are primarily statistical, and therefore there's room for even greater precision with additional data in the future. What about orbital angular momentum? Well, we have another parton distribution, a generalized parton distribution. It turns out this measures correlations between the longitudinal momentum of a quark or gluon and its transverse location in the proton. That's exactly what you need to look at spin-orbit effects, to look at orbital angular momentum. Gives access to the orbital angular momentum of the quarks and the gluons. And it turns out that exclusive J-psi production with transversely polarized protons provides access to a particular GPD, which is the one responsible for the orbital angular momentum of gluons. And data which we are recording right now in STAR will provide the only access worldwide to this generalized parton distribution, the only access worldwide to the orbital angular momentum of the gluons that we're going to have until the electron-ion collider turns on in something like a decade. Those measurements are starting right now. Let's go to transverse spin structure, and what's the time? Okay. Transverse spin asymmetries. Here are transverse spin asymmetries that have been measured for forward scattering of pi naughts over a wide range of energies, from center of mass energy of 20 JeV to center of mass energy of 200 JeV, and it turns out that even 500 JeV looks the same. There are large asymmetries up to 10% over a wide range of energies. Turns out that if you plug in naive, collinear, perturbative QCD, that predicts these asymmetries should be of order 0.1%. There are only 2 orders of magnitude bigger than that. That's a little embarrassing. So theorists went and decided it can't be in the scattering. It's got to be either an initial state effect or a final state effect. And these come up with fancy names these days that are based on the first theorist who proposed it. The initial state effect is called the Sivir's effect. The final state effect is called the Collins effect. And I'll explain both of them in a moment. Now, if we look at these asymmetries as a function of the transverse momentum of the pion which is produced, it's pretty flat with PT. And both of these mechanisms say that at sufficiently high PT, it should go down. We haven't seen that out to PT that are well past where theorists had expected it to be dropping off. So maybe it isn't anything we've come up with yet, and it might be something we haven't thought about. So what are these initial and final state effects? The Sivir's effect involves a correlation between the spin of my transversely polarized proton and the transverse momentum of the quark or gluon that enters into the collision. So we have a different probability of finding a quark or a gluon with its transverse momentum to the left of the spin direction or to the right of the spin direction. If that's true, then that transverse momentum, when it collides with a quark or gluon from the other proton, is going to produce a bias that we're going to get more jets produced on the side where the transverse momentum is bigger and fewer where it's smaller. This is sensitive to the transverse motion of the quarks and the gluons. It requires orbital motion, orbital angular momentum to be present in order to be non-zero. The signature ends up being an asymmetry in jets or photons, objects that don't involve splitting out final state particles. It turns out it is not a universal function. Remember I talked about universality. It turns out that there is an interesting sign change in the theory calculations that I'll talk about later. I may have to skip. The other mechanism is the Collins mechanism. I have my proton coming in. The proton is polarized, say, up. Inside my proton, I have a quark. And if my quark inside my proton is polarized either up or down, parallel or anti-parallel to the direction of the proton spin, that's called transversity. It's different from holicity. In a hard scattering, it turns out that that transverse polarization of the quark is largely preserved. So if I had it polarized up to begin with, it's polarized up coming out. Turns out that there is, when I have a quark with its polarization pointing up, if it then fragments into the final state hadrons that make up a jet, it does not do that in an azimuthally uniform manner. There is actually a significant azimuthal anisotropy in the pions that come out. If it's a pi plus, they're more on the left and fewer on the right. If it's a pi minus, they're more on the right and fewer on the left. This azimuthal anisotropy has been measured in E plus E minus collisions. It's called the Collins effect, and it's a signature tool to measure transversity because this Collins effect in the final state has been measured in E plus E minus. So by looking at the asymmetry in PP collisions, knowing what the asymmetry is here, we can work our way backwards to what the polarization, transverse polarization of the quark or anti-quark was back here. The measurement that I just described goes under the name Collins effect. There's another complementary measurement called interference fragmentation functions. The details are details. These are believed to be universal in contrast to these. So this transversity, I have my proton going to the right, the proton spin is up. Transversity is the difference between the probability of the proton spin pointing along, the quark spin pointing along the proton spin, or the quark spin pointing opposite to the proton spin. It turns out that transversity, you might think it's the same thing as helicity. I just rotated my frame. That's not true. It turns out when you look at the interaction, because of the chiral nature of the strong interaction, gluons have no transversity, whereas gluons have a significant helicity, as we've seen. In the meantime, the quark transversity is different from the helicity because here we're looking at effectively boosts from the momentum and rotations from the spin direction, and boosts and rotations don't commute. To date, this has only been measured in semi-inclusive deep-inelastic scattering, and there's much less data than for helicity. Here's the most recent global analysis. This is actually this one, done in 2013. You see the transversity of the up quark and the down quark and the uncertainty bands. I remind you, here are the analogous distributions for the helicity. You can see the huge difference in the precision. Well, just last fall, at the same conference where Starr and Phoenix showed the first 500 JeV results, Starr showed the first observations of transversity in PP collisions. These are the so-called interference fragmentation functions measured at 200 JeV in black and 500 JeV in red. These are the Collins effect for pi plus and pi minus. Blue is 200 JeV, red is 500 JeV. Comparable signals are seen in both channels at both energies. That provides a powerful test for universality and evolution effects. And these are the first ever observations of transversity in PP collisions. And these are actually the most precise measurements of transversity to date, although they have not yet been folded into a global analysis because they're too fresh. I told you that there might be an initial state effect in this forward asymmetry. I should note, these measurements are not at forward measurements. These are measurements at 90 degrees to the center of mass. Here we're back to the forward measurements. Here is a measurement for the total jet asymmetry. It's an order of magnitude smaller than the pion asymmetry. Here are expectations for data being recorded now and next year for direct photons. Photons don't involve fragmentation, so they have no final state effect, only initial state effect. And this are two methods to isolate the initial state effect. And what we're seeing is that it appears much smaller. It's only a small part of the asymmetries that we're seeing in the forward direction. Let's skip this, and let's just talk for just a moment about color interaction. This is this Sivir function that involves an initial state effect in actually in deep inelastic scattering. It is a final state effect. Here you're looking at the diagram where we have the virtual photon coming in, scattering off of a quark from our proton. And in order for the Sivir's effect to be non-zero, we have to allow for the fact that the scattered quark interacts with the spectators in the proton. And because if this is red, this is green and blue, and green and blue together is anti-red, we have red, anti-red, and color and anti-color attracts. This is an attractive final state interaction in QCD. If we shift and we look at an initial state, for example, we have a quark and an anti-quark interacting, producing, say, a virtual photon. That's the Drell-Yan process, or producing a vector meson, a W or a Z. In that case, when you track through the colors, you have the same color here, and here's this virtual interaction that has to be there for the spin effect to be present. And now it's red interacting with red. And like colors in QCD repel. So we have a repulsive interaction. And the difference between the attractive and the repulsive interaction produces a sign change in the predicted asymmetry here versus here. These have been measured in deep inelastic scattering. These have not yet been measured. However, at STAR, we did an exploratory measurement for vector boson production, W's in this case, with a small data set in 2011. The uncertainties are huge, but the data tends to be sitting positive, which actually is the correct sign for there to be a sign change. Similar measurements were done with Z's. They're incredibly clean, but very statistics challenged. We need a lot more data than this to explore this transverse momentum-dependent evolution effect, which is expected to be different from the evolution for the other quantities, and confirm or deny this Sivir sign change. That's proposed for 2016. Uncertainties look like these little bars down here. This transverse momentum-dependent evolution, this is the same sort of evolution that I talked about way back on, I think it was slide 6. Evolution for most quantities would be from the momenta that are looked at here to the momenta that are looked at here, maybe a factor of 2. But it turns out that theorists are concluding that transverse momentum-dependent distributions evolve a lot more rapidly, such that some people come up with a factor of 15. That would make it a much faster evolution, much more of this splitting process than in any other known process. Or maybe not, because it turns out this depends on the non-perturbative structure of the proton that has to be put in by hand from experimental data. And when you look carefully, it turns out we don't have the experimental data necessary to do that. We have to access similar observables at the same x, but very different momentum transfers. So we're looking at the same distribution with different scales, with different resolutions, with different degrees of splitting. And by combining direct photon measurements, which we're doing now, and DW measurements that we propose to do next year, we'll be able to either explicitly see this evolution, measure its magnitude. If it's less than a factor of 5, we will conclusively see whether the sign change is there or not. If it's more than a factor of 5, we'll conclude this is really small, and we've made a different discovery. And we'll combine with Brilliant in the further future. For time, let me skip this and go to the conclusion. RHIC spin program has found evidence for positive gluon polarization, found indications of an asymmetry in the polarized anti-quark C, and made the first observation of transversity in PP collision. And during the next decade, which we expect, by the way, to be the last decade of RHIC, we will measure gluon polarization down to 10 to the minus 3. We'll place strong constraints on the anti-quarks, get a first look at the gluon orbital angular momentum. We'll find the origin of the large transverse single spin asymmetries. We'll see these color interactions, attractive repulsive QCD interactions, and we'll test TMD evolution over a very broad range of splitting. In addition to all this, beginning in 1 month from today, we'll be starting to look at spin asymmetries in polarized p-gold collisions. That'll provide a unique probe of the saturation scale in heavy nuclei. That's the advertised spin observable. I actually came up with a crazy idea last week while I was sitting in the control room at STAR watching the data come in that I shared with the spin group earlier today, and we're going to try and do it. And we may end up with a unique probe of the hadronization process as well. We'll see. And the RHIC spin program is providing a bridge between the physics at RHIC and the physics for future electron-ion collider that will revisit these questions in about 10 years. Thank you. Lattice Qcd is a completely different talk. It's actually an interesting talk. I heard a great Lattice Qcd talk 3 weeks ago, and as Zoltan Fodor is ever in the country, you should get him here. Well, I'm thinking of it. Spectacular talk. Lattice Qcd, for those of you who don't know, is a tool that allows one to calculate quantum chromodynamics in the non-perturbative domain of strong coupling. Lattice Qcd provides, until very recently, Lattice Qcd calculated quantities only in the proton rest frame, not in essentially the light cone frame, which is where we're doing these measurements here. And it was not clear how one could make the connection between the two. Only in the past year has it been recognized how one can perform lattice calculations that can be directly tested with these experiments. Those calculations are underway right now. In terms of the calculations that are maybe most relevant at the moment, which are the lattice calculations for orbital angular momentum, it turns out that the lattice predicts that the up quarks actually carry a significant orbital angular momentum, maybe as much as 40% of the proton spin. The lattice also calculates that the d quarks carry a significant fraction. Orbital angular momentum carries a significant fraction of the proton spin, about 40%. And the lattice calculates they come in with opposite signs. So we get plus 0.4 minus 0.4. And we end up with a small difference of two large numbers out of lattice QCD for the orbital angular momentum contribution to the proton spin. And that may even be what the data are pointing toward here. Because if we extrapolate our gluon polarization measurements down to x equals 0, there are enormous uncertainties in that extrapolation. But if we just ignore the uncertainties and look at central values, we get about 30% of hbar. With the 0.15 hbar that we're getting in the quark sector, that's 0.45 hbar. That leaves about 10% of the proton spin for orbital angular momentum, and that can be quite consistent with the lattice calculation that come up with a small difference of large numbers. And beyond that, I think we need to see what the lattice tells us over the next year or two as these new tricks that have been recognized the past year get implemented. Right. So in the measurements that I talked about for the gluon polarization, what we measured is we start with a proton. We have its spin pointing, for example, if it's moving this way, we can choose whether its spin is pointing in the direction of motion, positive helicity, or opposite the direction of motion, negative helicity. We typically do half and half. Then we look at the, so this is the helicity of the proton. We then look at, we do that for both protons. So we have two protons. They come in with like helicity, or they come in with unlike helicity. Those have different cross sections. We've measured that difference in cross section. It's 1 or 2/10 of a percent in the high energy measurement for low momentum jets. It's as large as a 4% difference in the cross section at high momentum for the low energy, high energy jets in the 200 jet measurement. Having measured that difference in cross sections, the fractional difference in the cross sections, we then plug that into the QCD calculation, and we look at what comes out for the polarization of the quarks and the anti-quarks, and the answer ends up being that for our measurements, we provide no information at all about the polarization of the quarks beyond what was already there from deep inelastic scattering, but we provide a very dramatic reduction in the uncertainty in the polarization of the gluons. And what we see is that when a proton is coming along this way with its spin pointing this way, the gluon spins inside are also preferentially pointing that way. And the gluon spins inside the proton are contributing a significant fraction, ballpark half, of the total spin of the proton as a whole. Yes. So I have my proton. My proton is coming along. Okay, let me double back.